Today we're going to look at comparing two proportions instead of just a single proportion. And this will be the last chapter in this particular section in your book. So we're going to start off with an example. So a disease is killing many trees in a state near you. Random samples of trees from two different large forests, one at high elevation and one at low elevation, revealed that 36 of 24 trees at high elevation and 25 of 200 trees at low elevation died from the disease. Calculate and interpret a 90% confidence interval for the difference in the proportion of all trees in the state that have died from the disease at these elevations. Okay, so here's how we're going to start. So pretty easily we can find the difference between the observed proportions of the trees that have died. Okay, let P sub H be the proportion of trees that have died at high elevation from the disease, and P sub L be the proportion of trees that have died at low elevation from the disease. Then the observed difference in the proportions is found by, first of all, finding the observed proportion that died at high altitude, which was 0.15, and the observed proportion that died at a low elevation, which is 0.125. And the difference between the two is 0.025. It's a 2.5% difference between the two.
So it doesn't matter if the low goes first or the high goes first when you're subtracting?
It really doesn't. For the most part, we tend to do the bigger one minus the smaller one. I'll have to think about that a little bit. And when you're doing the problems, you typically want to specify things that I did the high elevation minus the low elevation or vice versa. Mm-hmm. So when you're working out the problem. So the problem is that there is a difference in our samples. But the samples are going to vary from one to another. So we'd like to get a confidence interval. All right, well, about how many what the proportion or the difference in the two proportions, what do we think that's going to be? So what we would like to know is the standard deviation of the sampling distributions for the difference in the sample proportions. And that is a lot of words, friends.
Yes.
Before we need to do that, we need to check some assumptions and conditions. The assumptions are similar to what we've been doing with some add-ons. First thing is the groups have to be independent of one another. Right? So in this example, we'll do that in just a second down here. The independence assumption, within each group, the data should be based on the results of independent individuals. Since we can't know this for certain, we impose the following two conditions. The randomization condition, that the data from each group should be drawn at random from the population, and the 10% condition, if the data are sampled without replacement. So some of you had some difficulties with this on the quiz, where you were doing the experiment with the explosives. That's not really, that's a population that we're sampling from. We're doing sample experiments. Okay, so there, it's like, well, how do you do 10%? There is no 10% for that, right? Because there's not a population. And then the sample size assumption, each of the groups must be large enough so that a normal model could be applied. So we're going to have our favorite old success failure conditions. Both groups must be big enough. And here we actually know how many successes and failures we have. So we're not going to do predicted successes and predicted failures. that baby has a concussion.
God,
It landed head first. There must be at least 10 successes and 10 failures observed in each of the two groups. Right? All right. So let's check to be certain, and this shouldn't be a question mark at the end of this. It should be a period. Check to be certain that the assumptions and conditions have been met in order to make inferences about trees in this state. All right. So the first thing, independent groups, and this is what people tend to leave out because everything else is pretty much like what it's been. So it's reasonable to assume that the trees at high elevation and those at low elevation are independent of one another. Now, before we go on, let's think about, well, is it possible that they aren't independent of each other? What could you think of that would make the ones at, say, the higher elevation affect the ones at the lower elevation?
They could be the same kind of tree.
No.
Oh.
So let's think about how a disease in trees might be transmitted.
Oh, through the roots. They got the same root system.
Spores.
Okay, could be roots, although they would, I mean, that would make it less likely that they would affect one another. Could be some sort of spores or some sort of bacteria or something. And might it be reasonable to think that that could roll downhill, as it were,
Yeah.
right? That if the whole lot of upper trees are affected, then it kind of, trickles down to the lower trees. Or if it is an airborne spore, is it possible that, especially on a mountain, where when the wind comes, there's an updraft, that it could carry those up? It's possible, right? But so I always want you to think about, all right, could it be that they're not independent? It could be. We don't know. We don't have any reason to believe that they're not independent, right? All right. So
That was a lot of science right there.
She doesn't like
A little bit too much science for me.
it's not so much science as it is, well, let's think about how they might not be. I mean, and biology is my weakest science going away. And so, but that's not a whole lot to think about. It's like, well,
So he's
Well, it's
basically
like
saying it's not a lot.
he said spores. I was like, what's a spore? I don't even remember what that is.
I don't even begin to know how to describe a
I was
spore.
thinking pore.
No, it's not like that. It's like these tiny little particles that a plant will. So if you ever stepped on a toadstool kind of mushroom where you stand and then all this like smoke looking stuff, you've never done this.
No. I do love mushrooms though.
There are some mushroom kinds of things where if you step on it, there'll be a little cloud of stuff. Those are all like billions of spores.
I've never seen that. It's cool.
You've never seen that?
We should go experiment.
I'll have to see if I can find the video. All right. So, and then it says it's random samples from 2 large forests. That's going to help us out. The samples are stated to be random. And from large forests. So our samples of size, what were the 2 sizes?
240 and 200.
Thank you. 240 and 200 are likely less than 10% of their respective forests. I was talking to somebody about this weekend. I don't remember who it was or why it even came up, but we're talking about how in statistics your wording is always hedging your bets. It's reasonable to assume it's likely that they're less. I mean, you're always doing things like that. Okay? And then each of these groups have to be big enough so that we get 10 successes and 10 failures. So for the low elevation, there were, how many were there? Low elevation 25 successes.
I think that's high elevation. Oh, yeah, you're right.
Okay. 25 successes. And therefore 175 failures. And at high elevation, there were, where are we? 36 and 204. All of which are greater than 10. All right. Okay. So now we need to talk about the standard deviation of the differences between the two proportions. This actually goes back to some stuff that we did earlier last semester. So if we have two samples of size N1 and N2 associated with sample proportions P1 and P2, the standard deviations of these are given the standard deviation of P hat sub 1 is, we've been doing this over and over and over again, the square root of PQ over N. Same for the second sample. Since these two proportions are taken from independent samples and are therefore independent, we know that the variance in P1, P2 is equal to the variance in P1 plus the variance in P2. Right? We always add variances. We never subtract variances, ever, ever, ever. We always add them. So adding those two variances together and then taking the square root, we get the standard deviation of P hat 1 minus P hat 2 is the square root of P1 Q1 over N1 plus P2 Q2 over N2. Unfortunately, we don't actually know the values of P1 and P2. Remember, that's for the whole population. We don't know how many trees in the high elevation and in the low elevation have died. So we'll use the observed proportions to estimate the standard deviation. We call that the standard error. So the standard error is the same thing, except it's the observed proportions instead of the actual proportions, which we don't know.
Oh, so standard deviation, standard error are the same thing. This error has to do with a sample, whereas standard
with standard error, we're estimating the standard deviation because we don't know it for the entire group.
Yes, that makes sense.
Yeah.
So
Yeah, you're taking that sample and you're using it to generate a standard deviation, and you're like, okay, and I'm going to assume that that's similar to the entire population. Okay?
So for the last problem, it would be 0.15 as for like, let's say, that was for low, or no, high. Be 0.15 times 0.85 over 240?
Yeah.
Okay, and then add plus the low. Okay.
Yeah. All right. So This is the sampling distribution model for a difference between two sample proportions. Provided that the sampled values are independent, the samples are independent, and that the sample size is large enough, this is the sampling distribution. P1 hat minus P2 hat is modeled by a normal model with the following parameters. The mean of P1 hat minus P2 hat is P1 minus P2, and the standard deviation of P1 hat minus P2 hat is given by, we've done this, it's just now we're adding those two together because those are both variances. But since we don't know the true proportions for P1 and P2, we use the observed proportions to estimate the mean and the standard deviation. We call that standard error. So go ahead.
So we can't actually find mean.
We're going to assume, well, we're not doing,
Or sorry, mu. Is that as well? Mu?
yeah, mu is,
It's not mean?
it is, it's the mean difference in these two proportions.
But we would never actually be able to find that because we would need the true.
Right, we don't know what it is. It's kind of what we're trying to figure out.
Okay.
All right. So the confidence interval is just like it's always been, right? We have the statistic plus or minus our z critical times the standard error. All right, we've done this before.
And the z critical will be the same for both.
I'm sorry?
The z critical would be the same for both.
It's one calculation.
Because 90%.
Yeah. Yeah. All right. So let's go back to our example. Let's calculate and interpret a 90% confidence interval for the difference in the proportion of all trees in the state that have died from the disease. All right. So our confidence interval is going to be equal to our observed difference, 0.025. That's our statistic. What do we know? Plus or minus, we want to do a 90% confidence interval. Now you can do that in your calculator. You can figure out what 90% is going to be by going down to distributions, doing a normal distribution. We're going to leave them at, the mean is 0 and the standard deviation is 1 because this is called a z interval. And because it's an interval, we want to get 90% to be in between the two. So I have to go back over here and go, all right, do in between the two and give me 90%. So that's 1.645. So 1.645 times our standard error, which is going to be the square root of, and this is what you were talking about a moment ago, Savannah. This is going to be 0.15 times 0.85 over 240 plus 0.125 times 0.875 over 200.
And I know May already asked this, but we always
It's okay.
keep the, we always keep the, what is it called? Oh, the statistic positive. Just always make it.
It could be negative.
Oh, okay.
Yeah, but we happen to do the high altitude minus the low altitude. So, all right. So, Bay, you're punching numbers frantically over there. Do you have values for us? What have you got?
So for the positive one, I got.
I'd like the negative one first.
Oh, okay. The negative one, I got .029.
.0.029?
Yeah.
Okay.
And then the positive one, I got .079.
Okay. So we're 90% confident that the actual difference lies in between those two, right?
Yes.
Notice what lies in between those two?
0.
0.
Oh.
Oh, so that could be the real one.
So there may be no difference at all. Our confidence interval points to, we don't have any confidence that it's not a difference of 0.
But nothing. Brody, when you said 0, Brody was like ready to start clapping, and no one else did, so it stopped.
No, I just figured it wasn't the time.
He was like,
There wasn't a long enough pause for me to start laughing.
that was good.
So that's the key. Okay. Pause longer, get more applause.
Yes, if you want me. Yes. Once you say something like, once you drop a bar, just like pause for a second, and then I'll start.
Brody's gonna be like,
Hey,
So,
"Dude."
although this isn't a hypothesis test, it can tell us something about what we would get from a hypothesis test. Okay? So, your book is big on this. The AP exam is not as big on that. About, working with a confidence interval and then asking about, what do you get from that? But, I mean, 0's in there. So I'm like, it's in my confidence interval. It certainly could be the actual difference in those.
And so then, if you're negative, does that mean like you're below the actual standard deviation?
No, the actual standard deviation.
Or
These are proportions.
oh yeah, the proportion.
The difference in the two proportions.
Yes.
So if the difference in the two proportions is negative, that means that the high actually had less than the low. If it's positive, the high had more than the low. Yeah, you're thinking about this too much. Oh, hang on a second. We did it right here. We did the high minus the low.
Yeah. Oh.
So it's possible that the high minus the low is actually negative, that the high actually has less than the low does.
That makes sense. I see what you mean.
And it's also possible that the low has,
More.
well, the high has less would be the same thing as saying the low has more, right? So both of those are possible. So I can't really glean anything from that. And I was immediately suspicious the first time I saw this problem when I was like, there's only a difference of 2.5%, and these are not super big samples. Now, if these were enormous samples and we got this 2.5%, then perhaps this might be statistically significant. But it doesn't appear so. All right, let's do a little bit on page 3 real quickly. These are on your formula sheet, and this is the way that they look. So we're talking about this part right here. So the mean difference between the two is the difference between those two proportions. And this is the actual standard deviation, which we typically can't do. We have to do the standard error. We'll talk about this part about when P1 equals P2 is assumed tomorrow. We'll finish that. I think I'm supposed to do 2 days on this. Now I'm questioning myself. Self? Oh, there we go. Yeah.
So for the mu that you have, I know there's like a proportion, because it's like a sample proportion 1 minus sample proportion 2. That equals is, we're assuming that's going to equal the actual proportion, like the actual whole entire population.
Yeah.
Okay.
All right. Any questions about that?
No.
Okay.